We'll start now?
Yes, Maya.
Okay.
Professor Baghla, we'll start.
Yes, please.
Okay.
Good afternoon, everyone. I am Mayank, student coordinator of Asteria Club. Firstly, thank you all of you for joining today on this astronomical lecture series on black hole, which is organized by Asteria Club DSU-SOE Asteria in association with Department of Physics. We are pleased to welcome those of you who have been with us for some time now, as well as those who will be joining to our community or group. Just before we get started, I would like to express my gratitude to all of you who are so generously helped us to make this event come together smoothly. I would like to thank Vice Chancellor Professor Murthy, Registrar Dr. Puttamadda, and Dean SOE Srinivas. And I would like to thank Dr. Radhika. I request student coordinator Hariharan to give a brief introduction about Professor Baghla.
Good afternoon, everyone. Professor Jasjeet Singh Baghla was born in Agra and did his education from Delhi. As a research scholar at Inter-University Centre for Astronomy and Astrophysics, Ayuka, Pune, he pursued his PhD on gravitational clustering in an expanding universe. He took up a postdoctoral research associate position at a prestigious institution like Institute of Astronomy in Cambridge, UK, and the Edward Smithsonian Center of Astrophysics, US. He had worked as a faculty at Physics Department of Harish Chandra Research Institute, HRI, in Allahabad, before moving on to the Indian Institute of Education and Research, IISER, Mohali. He is present professor for physics and Dean Academics at IISER, Mohali.
Okay, thank you, Hariharan. So today, as we are enlightened with the presence of distinguished speaker Professor Baghla, I request him to share his insight with us. And in the meanwhile, if any of the students have any of the doubts, they can just post on the comment. We'll do it in later, at the end of the session. Over to you, sir.
Thank you. Thank you so much for organizing this event and for the kind introduction. I will be speaking about Nobel Prize in Physics 2020. And as you are aware, the prize was divided between three people. Roger Penrose from Oxford got half share, and Reinhard Genzel at Max Planck Extraterrestrial Physics in Garching, and Andrea Mia-Ghez at UCLA, they got 1/4 each. The work is divided into two parts. Roger Penrose's work was highly theoretical, and Reinhard Genzel and Andrea Mia-Ghez are both observers, and their work is observational. But both essentially try to focus on possibility of black holes. Roger Penrose demonstrated that it is possible to make a black hole, so to speak, through natural astrophysical processes, that a black hole can form from astrophysical processes. And Reinhard Genzel and Andrea Mia-Ghez have been observing the center of our own galaxy now for almost 30 years to establish that there is a supermassive black hole which is present at the center of our own galaxy. The proof isn't there yet, and I will show you the observations to help you make sense of what I'm saying right now. So the talk will be divided in two parts. One for the work done by Roger Penrose and the other by Reinhard Genzel and Andrea Ghez. So citation for these two halves is also different. For Roger Penrose, the citation, Nobel Prize citation, is that the award is be given for the discovery that black hole formation is a robust prediction of the general theory of relativity. And for Reinhard Genzel and Andrea Ghez, it's for the discovery of a supermassive compact object at the center of our galaxy. Notice how they use a lot of heavy words, but skip the phrase black hole for the second half. So let's talk about Roger Penrose first. He was born in 1931. He is an emeritus professor at the University of Oxford. He is in the Department of Mathematics. He was born in Essex, trained as a mathematician, graduated from University College London, and did his PhD in 1958 from Cambridge University on tensor methods in algebraic geometry with John Todd. And in his early work, he introduced the use of topology of light cones to study spacetimes. So let's start with the beginning in the story of black holes. Okay. So black holes are about extreme gravitating objects. So let us first talk about gravity. The gravity was conceptualized as a universal force in the 17th century by Sir Isaac Newton. It's going to be almost 350 years now since it is 350 years indeed, since he came up with the idea. And this idea of a universal gravitational force was successful in explaining planetary motions and many terrestrial phenomena. And gradually, scientists started to analyze implications of gravitational force. Discovery of Neptune in 1846, as predicted by astronomers, was a very high point amongst many successes of Newtonian theory of gravity. It essentially made people believe pretty much anything which you could calculate with this. So much so that at some stage a physicist said somewhere in the 19th century that, you give me the precise locations and velocities of all the particles in the universe at some time, and I will predict the infinite future for you exactly. Very, very brave words. The other key ingredient in study of black holes, because it concerns inability of light to escape, is the speed of light. And it was an astronomer from Denmark, Romer, who was the first person to measure the speed of light. And he did so by observing eclipses of Io, which is a satellite of Jupiter. The time period between eclipses appeared different depending on whether the Earth was approaching Jupiter or whether it was going away from Jupiter. And Romer conjectured that this was essentially some kind of an effect of a finite speed of light. We understand it to be the Doppler effect in some sense. And he used it to measure the speed of light. He did not get the correct number, but he got the correct order of magnitude. He was well within a factor of 2. So once these two numbers were in, it was natural that people will conjecture about various things. And these two gentlemen, John Michell and Laplace, these two people conjectured about extreme gravity and dark stars. So Michell, for example, talked about, so this is from his publication, that hence, according to Article 10, if the semi-diameter is radius and S was written as F, semi-diameter of a sphere of the same density with the sun were to exceed that of the sun in the proportion of 500 to 1, a body falling from an infinite height would have acquired at its surface a greater velocity than that of light. And consequently, supposing light to be attracted by the same force in proportion to with its inertia with other bodies, all light emitted from such a body would be made to return towards it by its own proper gravity. So essentially what he was saying was that light cannot escape. And then he went on to say that for all you know, the universe could be full of objects which are very massive but not luminous. And he said that while we will not be able to see such dark stars, but their gravity will be strong. And therefore, if we observe orbits of things in the vicinity of such objects, we may be able to deduce their presence. Very, very prescient, as we will see in the second half of this talk. And Laplace, writing in French, came up with some similar predictions. Okay. So these are all more than 200 years ago. And you're all familiar with the concept of escape velocity. If I launch something from the surface of Earth with a given speed, typically it will go up to a certain height and fall back, unless I give it enough energy so that it escapes gravity, in which case the energy of the object has to be positive. It should not be bound to gravity of whichever object it is being launched from. And by putting the condition that energy, total energy is zero, that gives us the escape velocity. Anything larger than that will have the object escape from the gravity. So the formula for escape is square root of 2gm by r. And if the escape velocity is speed of light, then r is 2gm by c square. So this is a very crucial formula, and we will see it again and again in this talk. So things remained for some time until Einstein came up with his own theory of gravity. And Einstein argued that gravity should not be treated as a force. Instead, gravitational effect modifies space-time in the vicinity of objects. Other objects move in this curved space-time, and Einstein's theory tells us how space-time gets modified and also how particles move in a curved space-time. Special relativity, it was realized, is applicable in small regions in freely falling frames. So for example, if there is a spacecraft like the space station, which is going around the Earth, it is falling freely, and therefore inside the space station, I should be able to treat it as a very small inertial frame. And that is why astronauts in the space station do not feel any gravity, because the whole system is falling freely. The first prediction for black holes came from Carl Schwarzschild. It's interesting that he was actually fighting in the First World War, and much of the calculations were done when he was recovering from an injury. This was the first exact solution in general theory of relativity. He assumed spherical symmetry and time independence, and he found that the solution has a singularity. And there is also what we now call as a horizon around the singularity from which nothing can escape. It turns out that the radius of this horizon is exactly the radius which we calculated 2 slides ago, which is 2gm by c square. At that time, there was no clear understanding of what it meant, and people actually felt that there are 2 singularities in Schwarzschild's solution, one at the horizon, and the other at the center at the origin. So if you have a solar black hole which has got a mass of 3 times the mass of the sun, then the horizon will be at a distance of about 9 kilometers. For Earth, it is at a radius of 3 kilometers. For Sun, it is at a radius of 3 kilometers. And for Earth, it will have a radius of 9 millimeters, which is exceedingly tiny. And around the black hole, about 1.5 times this particular radius, which is called the horizon radius or the Schwarzschild radius, at 1.5 times this radius, there is something called a photon sphere. So a photon can go into a circular orbit around a black hole like this. So the event horizon is at 2gm by c square. And in honor of Schwarzschild, this is often called the Schwarzschild radius. Nothing can escape from the event horizon, and things can only fall in. And therefore, this is a one-way membrane. I should caution you that this interpretation, that it is a one-way membrane, came much, much later, and Penrose had an important role to play in that realization. Photons can be in a circular orbit at a radius 1.5 times the Schwarzschild radius. This is called a photon sphere. The smallest stable circular orbit for massive particles is at a radius of 3 times the Schwarzschild radius. So there can be no stable orbit, stable periodic orbit with the approach to the center smaller than 3 times the Schwarzschild radius. And unlike Newtonian mechanics, even particles with a non-zero angular momentum can fall to the center as the centrifugal barrier does not extend to infinite energy. Now you are all familiar with this, that when we look at the problem of gravitation and orbits of gravitating systems of two particles which are attracting each other with gravity, we know that there is an effective potential, there is a 1 by r potential for attractive force, and there is a 1 by r square repulsive centrifugal energy corresponding to the finite angular momentum. And therefore, as you go to r very, very small, it is the centrifugal energy which always dominates, and that creates a barrier, which means unless the angular momentum is zero, the orbiting particles cannot come to zero separation. In relativistic mechanics, the effective gravitational force is different from 1 by r square at small r, which means the effective potential has terms which are like 1 by r square and 1 by r cube. And because of that, even with a non-zero angular momentum, things can fall to the center. Schwarzschild also found solution for a star, although understanding at that time was not very clear. And in this case, he again assumed spherical symmetry, and he found that the problem of horizon disappears and there is no singularity at the center. But there was no clear understanding of this particular thing. And of course, the interior solution depends on details of density, pressure, and how these vary with distance from the center. So Schwarzschild did his work in 1918, and there was some follow-up work. He unfortunately died shortly after because of an illness. And no one really took black holes very, very seriously till at that point of time, even though people started taking the theory of relativity very seriously. In 1930-31, Subramanian Chandrasekhar, he pointed out that white dwarf stars cannot have a mass more than 1.4 times the mass of the sun and still be stable, which means that if you take a white dwarf star and keep on throwing some mass into it, the moment it crosses 1.4 times the mass of the sun, it will collapse it will suddenly begin to collapse. This limit was of 1.4 times the mass of the sun is named after Chandrasekhar, and it was derived by combining special relativity and quantum statistics. Both were, special relativity had been around, but quantum statistics was relatively new, having been discovered by Dirac and Fermi in late 1920s. So the obvious question which people asked was, what happens if a white dwarf of a larger mass forms, or if a white dwarf star gains some mass? Some people conjectured that maybe it becomes a neutron star, which is much more compact, but these conjectures came later. And because no one knew an answer to this question as to what happens if you cross the limit, there was a lot of opposition to Chandrasekhar, including from his supervisor, Eddington. So Chandrasekhar's work was in 1930-31. A little while later, a few years later, Vishweshwar Dutt from Presidency College, he discovered the analytical solution for collapse of a pressureless spherical ball of dust. So this was the first time-dependent solution. Unfortunately, he died in a hernia surgery, and the work remained unknown to most people. His solution was published in 1997 by the Journal of General Relativity and Gravitation as a golden oldie, as a special paper. Independently, Oppenheimer and Schneider. Oppenheimer went on to work in the Los Alamos project, the Manhattan project for building the first nuclear bomb. You can see his picture over here. Oppenheimer and Schneider independently discovered the same solution in 1939, while Vishweshwar Dutt's main interest was actually not in collapsing but expanding spherical ball of dust. Oppenheimer interpreted their own results, and they showed that if you can start with a sphere of pressureless dust, and it will collapse and it will form a black hole as well as a event horizon. But people said that, look, hey, dust is not something which stars are made of. Stars are made of gas. It's hot gas and it has pressure. So what will be the effect of pressure? Is it kind of impossible to resist this collapse and form black holes, or will black holes form? So that question still remained an open one. Stepping into this game in 1950s, a very, very critical role was played by Professor Amal Kumar Raychaudhuri. He, at that stage, was working at the Ashutosh College. Ashutosh College in Calcutta. And he studied the local properties of flows in general theory of relativity. And he demonstrated that local behavior can always be decomposed into convergence or divergence. So things are kind of coming close, or they are going away, or there is a rotation, or there is a shear kind of pulling apart. And once you write down things in this form, Raychaudhuri was able to demonstrate that in the kind of models that people had been working on for cosmology, or the Oppenheimer-Schneider model and so on, it became fairly clear that the presence of pressure will not matter much and a black hole will form. But that is where matters remained. Unfortunately, there was a wrong calculation which was done by some people, one Russian group, which became popular and which seemed to suggest that black holes cannot form. And that became popular for about 7-8 years until Roger Penrose were able to demonstrate that they had made a mistake. And then, of course, they also realized their mistake and they retracted their paper. But now, about 10 years after Raychaudhuri's work, there was an astronomical reason for taking black holes seriously. And this came because Martin Schmidt, he found the redshift of an optical star-like object associated with a radio source discovered in Cambridge. The radio source is called 3C273. And he found that the redshift is 0.158, which was a record breaker for its time. And this essentially indicated that this particular source is really, really far away from us. Okay? So if I were to do a quick calculation in my head, it will be of the order of about 100 million light years away from us. And with that kind of a distance and the object being fairly bright, the only viable explanation for the source of energy was that there is matter which is sinking in towards a black hole. And if it doesn't sink in straight away, but it goes in with some angular momentum, then it forms a disk around the black hole, and matter heats up in this disk to very high temperature, and that can give rise to the emission which we see. So that was the conjecture that people came up with in early 1960s. And this was one of the reasons why Penrose got interested, at least intrigued by the possibility of black holes. So one of the things which Penrose did was to first study Schwarzschild's solution and study it by using different coordinate systems than had been used by Schwarzschild himself. He pointed out that gravity distorts the light cone structure, and the distortion becomes so extreme that for an infalling particle, all possible trajectories lead towards the center once it crosses the horizon at the Schwarzschild radius. Now, this is something which was kind of known but not mathematically demonstrated. And Penrose used a coordinate transformation to give a very clear coordinate transformation to give a very clear demonstration of this. There is a graphical representation which you can see over here. Now, he published this work and he called it as Eddington-Finkelstein coordinates, even though the work was done by him. He said that the idea was given to him by Eddington and by Finkelstein. So what Penrose did was he said that, okay, so the horizon at Schwarzschild radius is a trapped surface in the sense that the moment you go in, you cannot come out, but otherwise there is nothing wrong or nothing singular or nothing drastic happening at such a place. He then expanded this idea using topological constructs with the Raychaudhuri equation, and he showed that if in any space-time you form trapped surfaces like the horizon in Schwarzschild radius, it is inevitable that within that a singularity will form. Okay, so that means that if you can form a horizon, there is an inevitable formation of a singularity at the center. Singularity essentially means that all the physical quantities will diverge and become infinite. Unfortunately, the theory also tends to break down at such places. And it was interesting that around the same time, Roy Kerr had found a solution for a rotating black hole. And this too had trapped surfaces. And so the proof which Roger Penrose gave was taken with more enthusiasm because for the first time, there was a solution for black holes other than the Schwarzschild black hole. So it became clear that the spherical symmetry which Schwarzschild solution demanded was not a requirement for forming a black hole, because people would say that, you know, every star has some rotation. So if you try to form a black hole out of a star, there will always be some angular momentum, and therefore there will be some departure from spherical symmetry. But with Roy Kerr's solution, it became clear that absolute spherical symmetry was not required. Now, Penrose did not show whether formation of trapped surfaces itself is inevitable in any collapse. Okay, so as I said, he showed that if trapped surfaces form, then a singularity will form inside it. But he was not able to show that if a singularity forms, it will be surrounded by trapped surfaces. And that is still a conjecture given by him, which is called the cosmic censorship conjecture, that singularity is always surrounded by trapped surfaces. It is clothed in trapped surfaces, and there is no naked singularity. Roger Penrose has also made many other contributions in physics and other fields. For example, Stephen Hawking worked with him on generalization of singularity theory to cosmological context, showing that the early universe must have had a singularity. He also gave something called the Penrose process, which shows that one can, in principle, extract energy from a rotating black hole, like a Kerr black hole. And he worked on impossible geometrical constructs with the famous artist IISER. You might have seen his things. So there's an impossible triangle which is drawn over here. He came up with a tiling with five-fold symmetry, which is shown at the bottom right. And in 1990s, people discovered quasi-crystals with five-fold symmetry. It was thought that when they got the Nobel Prize, Roger Penrose should have got a Nobel Prize as well at the same time. Unfortunately, he did. It would have been interesting if he had got a Nobel Prize for chemistry as well as physics, seeing that he is actually a mathematician sitting in a mathematics department. So science really does not know any departmental boundaries, and people, great thinkers, can contribute to many, many diverse fields. Coming to the second part, which is a black hole in the galaxy, and I have put it in quotes because, as I mentioned, the citation does not mention the phrase black hole. It talks about the discovery of a supermassive compact object at the center of our galaxy. So there's also a picture of Andrea Ghez and Reinhard Genzel. Now, back in 1980s, people had started discovering evidence for black holes in centers of galaxies. And it was also known that the black hole mass is correlated with the mass of the bulge in spiral galaxies. You can see a picture which shows the bulge mass of galaxies on the x-axis in units of the mass of the sun, and black hole mass on the y-axis, again in the units of mass of the sun. And you can see that they are correlated. For elliptical galaxies, the correlation is with the full galaxy mass because there is no spiral disk and the entire galaxy can be treated as a bulge. And you can also see from this relation that black holes could be as massive as 1 billion times the mass of the sun. Of course, within our own galaxy, the bulge mass is small. It's around 10 to the 9 times the mass of the sun. So the black hole mass is correspondingly lower. It is about 3 times, 3 million times the mass of the sun. Now, with these kinds of studies, it was expected that there is a black hole at the center of our own galaxy. The question was, how do we see it? So if we take a look towards within the plane of our own galaxy, focusing towards, so the center of the galaxy is in the middle of this frame. And this is pictures are taken in different wavebands, starting with very low frequencies at 408 megahertz on the top and gamma rays at the bottom. Now, if you do a quick scan through all of these, what you find is that it is only in the near infrared that one is able to, in the near infrared or in infrared, that one is able to see objects near the center of the galaxy without any obstruction. In all the other bands, there seems to be some obstruction or the other, or you don't see stars. There is no obstruction, but you don't see stars, or there is an obstruction. It's only in the near infrared that there is some obstruction, but you can see stars towards the center of our galaxy. To illustrate that, if you look at the 4th row from the bottom, you will notice that this is the only one in which you can see the central bulge. Okay. In all the others, the bulge is heavily obscured or not visible at all. So this is the set of wavelengths which was chosen by observers. So Reinhard Genzel was the first one to start observations, and Andrea Ghez followed shortly. The idea was you image the center of the galaxy, search for stars near the center, and use observations to infer mass distribution near the center. And scattering due to dust causes significant reduction in flux. So in the near infrared, where K-band, where the observations are done, by these two groups, the reduction in flux is by a factor of 1,000. So they are, whatever they are seeing, the objects are actually 1,000 times brighter, but the intervening dust and gas clouds absorb 99.9% of the light, letting only 0.1% of the light through. Seems like a very small fraction of light which comes through, but in all the other wavebands, it is much worse. The other difficulty is due to the turbulent atmosphere, which makes all the images rather fuzzy. So initially, observers use something called speckle imaging, where they take very, very short exposures and then combine them. But eventually, they had to move to what is called adaptive optics to make further progress. So what happens is that when light from a distant source enters our own atmosphere, the lower layers of atmosphere, the lowest 10 kilometers or so, are highly turbulent. Any of you who has ever been in a long distance flight would know that there are times when the plane just kind of starts shaking. and you are ordered to go back to your seats, put on your seat belts, and sit straight. So the turbulence not only shakes up airplanes, what it does is that it distorts the plane wavefront which is coming from distant astronomical objects. So where you design your telescopes and optics to deal with a plane wavefront, in reality you have a disturbed wavefront, and the kind of disturbance keeps on changing with time. So what adaptive optics tries to do is to try and figure out what is the disturbance or what is the effect of that disturbance on plane wave fronts, and uh, modify or remodify the wavefront to make it plane again. For this, the wavefront has to be sensed and corrected. Both have to be done in real time, and therefore these require very fast computers to be working in conjunction with the telescope. But the price of being able to do this is that your images which you construct are much, much better. So to illustrate the idea a little bit further, you can think of taking a perturbed wavefront, which is not plane, should have been plane, but it is not plane because of disturbances in the atmosphere. Now you put a lot of lenses in front of that, and you try to look at the image of a bright star. Because the wavefront is perturbed and not plane, it is tilted, the image of the star will form at different place for each lens. But if you know where the star should have been, you know what is the displacement. And from this displacement, you can reconstruct the wavefront, the perturbed wavefront. And then you have to put a mirror in the path of light, which will correct this disturbance. That is the basic idea of adaptive optics. Since every field of view does not have bright stars, astronomers remedy the situation by creating a star by focusing laser beam in the upper atmosphere above the turbulent layer and imaging that instead. So this is the very first image made using adaptive optics. This is from 1989. It was published in 1990. You can see that in the left image, where there is no adaptive optics, you see some fuzzy object, but a single object. On the right-hand side, where you can see two distinct images, one bright on the left, one fainter one on the right, that higher resolution going below the resolution of 1 arcsecond is the result of adaptive optics. So what adaptive optics allowed these astronomers to do is to image stars very close to the compact object at the center of the galaxy. And for about 30 years, you will notice that in this particular plot, on the right-hand side, orbit of a star is plotted. And there are crosses and observations corresponding to different dates. The first one is in 1992. So observers, so this is the remarkable work which they have been doing. They have been observing stars orbiting the central compact object, supermassive compact object. Now you have the orbit, you have the orbital parameters, you have the time period. From there, you can ask how much mass is contained inside this orbit. And that is basically what we need to do. Unfortunately, the movie is not going to play in this particular mode. I will try and see if I can show you the movie later, but the essential points are already conveyed to you. So this is an image of the Galactic Centre done with adaptive optics. Now, as we go towards the center of the Milky Way, on the x-axis is distance from the center in logarithmic units. On the y-axis is the mass, again in logarithmic units, in units of mass of the sun. So you can see that as we go in, the mass contained within a given radius is decreasing. And the first set of points are at log r in kiloparsecs of 0, which means radius of 1 kiloparsec, which is about 3,260 light years from the center. At that stage, the mass enclosed is a little bit more than 1 billion times the mass of the sun. By observing stars around the central object in the center of the galaxy, people have been able to construct orbits. So there are some more stars which have been observed. S62 is the most remarkable one, which has a very short time period. So what one can do is, from each one of them, one can estimate the mass contained inside the orbit. So on the x-axis over here is the distance from the central object. On the y-axis is the enclosed mass. And you can see that as we go towards the center, mass comes down and then it kind of levels off. The stars observed by these two groups are over here, from S62 to S stars. So what these people have managed to do is to push the edge from somewhere around 10 to the 5 times the Schwarzschild radius down to about 10 to the 2 times the Schwarzschild radius. So they have pushed the frontier by a factor of 1,000, but they are still a factor of 100 or so, 200 out from the event horizon, which is why we cannot say that they have discovered a black hole or they have proven the existence of a black hole. What they have proven is that within the region corresponding to about 200 times the event horizon, the enclosed mass is about 4 million times the mass of the sun. There are some observations in X-rays and infrared and radio, which are from smaller radii, but they are unable to make any decent mass measurement. You can see that the error bars on the X-ray hotspot and IR flare are themselves spanning almost 1 full order of magnitude. So this is, in some sense, the essence and summary of the result of 30 years of work by 2 teams using some of the largest telescopes in the world, and they have managed to make a very convincing case for presence of a very massive object at the center of the galaxy. And the current estimate is that it is 4.15 million times the mass of the sun. So the current status is that they have even gone on to measure gravitational redshift for stars in the vicinity of the central object. They have measured precession of orbits due to relativistic corrections. And these verify the space-time geometry in the weak field limit. K-band interferometry with 10-meter class telescopes has improved sensitivity, and results are likely to improve further in future. So this is the summary. The Nobel Prize 2020 recognizes theoretical advancements and observational work that established black holes as astrophysical objects. The citation unfortunately shies away from stating that Genzel and Ghez have established the presence of a black hole. Roy Kerr, who gave the rotating black hole solution, thankfully he is still alive. We hope that he will be around for some more years, and therefore he can be awarded for his work as well. And the Event Horizon Telescope, which imaged a black hole in M87, they perhaps have a stronger claim on that particular count. So I will stop here. Thank you so much for your patience and listening. I'll be happy to take questions.
Okay, so now I request Yoganshu to ask the questions.
Thanks, Mayank. So now we are open for question and answer session. So if any faculty or the organizing committee members have any questions, they can unmute themselves and can speak up, or they can type in a chat box. Also, rest of the audience are requested to type their doubts or the questions in the live chats.
I think you should start with the 2 research scholars who have been working on black holes.
Sir.
Yes, Purna.
So the image of black hole which we have obtained from Event Horizon Telescope,
Yes.
do we get any physical information from that except the I mean, obviously we get the visual representation. Other than that, do we get any physics information from that, just from the image?
Yeah. So I had mentioned in my talk that there is a photon sphere at 1.5 times the Schwarzschild radius. And that is a state, that is a distance at which a photon can orbit a black hole. Now that is for a circular orbit, but you can do a more detailed calculation of what kind of trajectories will photons have in the vicinity of a black hole. And what you find is that if you watch a black hole from a distance, and if it is kind of surrounded by objects which are emitting light, because of bending of light by black holes, you will see emitting objects, but you will see a hole in the middle, which has a radius which is of around 1.5 times the Schwarzschild radius. Small variations around that are expected, depending on exactly where emitters are located. But broadly, that is it, and that is what has been seen. So essentially, from the radius of the dark hole in the middle in the Event Horizon Telescope image, you can straight away estimate the mass of the black hole. That is the physical information that you get. By adding more observations and looking at time variations, they can say something about the distribution of emitters in the vicinity of this black hole. But that data is still being analyzed. I think some part has been released, but not a whole lot. And it'll come through in the next few years. I hope I have answered your question.
Yes, sir. Okay, thank you, sir.
You're welcome.
So I can see some of the questions in the chat. So Raghavendra Rao is asking, what about supermassive black holes?
Yeah, so supermassive black holes are those which are much more massive than a single star. So the black hole at the center of our galaxy is 4 million times the mass of the sun. So it is a supermassive black hole. And the black hole at the center of M87, which was imaged by the Event Horizon Telescope, is more than 1 billion times the mass of the sun, which that is also a supermassive black hole. As far as we can tell, pretty much every galaxy worth its name has a supermassive black hole at the center. So I don't know if this was the question or whether he wanted to ask something else.
Okay, so next question is from Khushi K. So can the black hole bend the space-time fabric and affect humans directly?
Well, if you go very close to it, yes, but not otherwise. It does bend space-time in the vicinity, and as I said, photon trajectories. I mean, light is supposed to travel in a straight line. Photons are supposed to travel in a straight line, but they can get into a circular orbit very close to the black hole, and their trajectories are bent so much that they may be doing a few loops around the black hole before coming to us. So space-time is definitely distorted, but it affects human beings only if they get too close to a black hole, not otherwise.
Okay, so next is, can you explain the Hawking radiation?
Okay. Hawking radiation takes us away from the realm of classical gravity to set the history in some, kind of put it in some context. In 1970s, early 1970s, people had been looking at properties of black holes. And if you recall the formula for radius of the black hole, it was 2gm by c square. So what people pointed out was that the radius is proportional to the mass, which means the area of a black hole or the area of an event horizon is proportional to mass square. And if I were to calculate effective density, density is not a constant, it also depends on mass, being very high for low masses, but being low for high masses. So these were things which people were pondering about. And then they asked, what happens if two black holes merge? So mass in an ideal case will go from m1 and m2 to m1 plus m2. Radius will go from r1 and r2 to r1 plus r2. And area, which will be r1 plus r2 whole square, is going to be more than r1 square plus r2 square. This led one great physicist, Jacob Bekenstein, to conjecture that maybe we can treat the area of black hole as entropy. He made further progress and he showed that one can treat the mass of a black hole, inverse mass of a black hole, as effective temperature. So he started looking for thermodynamic analogs of properties of black holes. And once you start doing that, anyone who has done physics will know that next step beyond thermodynamics is statistical mechanics, and people start looking at what are the microstates which correspond to this and how do I understand it in terms of quantum physics. So this was the scenario where Stephen Hawking stepped in, because obvious question once you ascribe a temperature to a black hole was, will it radiate? And what Hawking did was to do a calculation of a field of particles, so quantum field in the vicinity of a black hole. And it turns out that when we go to relativistic quantum mechanics, which is essentially quantum field theory, we can no longer describe a single particle. The universe always has an infinite number of particles and states. So what Hawking found was that there is always, even in vacuum, there is this pair creation annihilation happening, which contributes to various phenomena. But in the vicinity of a black hole, every pair which is created may not annihilate, because one partner can fall inside the black hole while the other one may remain outside. So that was an interesting possibility, and he asked the question as to what will happen if I have a distant observer looking towards this black hole. What kind of a radiation will that person see? It turns out that they will see a black body radiation corresponding to the thermodynamic temperature that Bekenstein had calculated. So this is Hawking radiation. Because the thermodynamic temperature is inversely proportional to the mass, the radiation from very massive black holes is negligible, and it kind of speeds up. It becomes higher as the mass goes down. So if you take Hawking's calculation seriously, then the prediction would be that all the black holes are radiating light, black body radiation, and because of which they are losing energy, and therefore they may be disappearing, and they may suddenly evaporate. So this is Hawking radiation.
Thanks for the explanation. So next question is quite interesting for the youth, I think. Will the black holes take into another dimension as shown in the fantasy movies?
Well, a rotating black hole has many trapped surfaces, and it turns out that it is possible to get into regions between different trapped surfaces. This is where Penrose process of extracting energy from a black hole works. But as far as we know, they don't take you into another dimension. No.
Thank you, sir. So as you said, telescope can give us the approx radius. So I get this next question from Inesh Rao. So how can we learn about black holes if they trap light and cannot be seen?
Yeah, so going back to the prediction of John Michell, who said that, you look at objects in the vicinity of a black hole, and through their motion, you can deduce what is there. That is what Andrea Ghez and others have been doing, and they've got a Nobel Prize for that. The other possibility is to look at light coming from the vicinity of a black hole, and that is what the Event Horizon Telescope people are doing. Both of these give us a very clear idea of what is there. These are essentially So what you are doing is you are predicting from theoretical point of view as to if you try to see something in the vicinity of a black hole, what you see, and then you observe something, and if it matches, you say that these are consistent with each other. So that is how you make progress. And once you say that they are consistent with each other, then you ask, what are the other things which the same calculation predicts, or can I take the calculation further? You keep doing it until it breaks. When it breaks, you know that you need to revise your theory.
Okay, so next is from Nachiket SU. Do rogue black holes really exist?
Can you define rogue black holes?
Okay, by the time he defines, I think we can move to next question. So, is time travel through black holes real?
So I think this student who is asking this question, so they have watched the Interstellar movie. So they see this guy jumping through a black hole, coming out of a wormhole, and then he was, at the end, it is like he was actually in the room of his daughter.
No. So, see, wormholes are valid solutions in Einstein's theory of relativity, but the same solutions also tell you that nothing of a finite size can pass through a wormhole. So essentially, fiction is adding some bit of imagination and using a poetic license to show you something.
Yeah, but then that brings me to a question. Then why people like Kip Thorne, who they do understand all these solutions which had been existing, why did they create that animation for the movie? Why that would have happened?
Well, what Kip Thorne and all did was to create a realistic view of the black hole that the spaceship will see. They did not work on the wormhole part.
Mm. Yeah, but yeah, correct. That came by the
Yeah.
director and others. Correct, true. Yeah. So I think most of his questions are that only, and he's asking about the image. So I think the image is already there. So, Karthik, I guess his name. So Karthik, the black holes have been already imaged. That's the Event Horizon Telescope. It has imaged it. So you can just search for it. You will be able to see the image. Now, I have a question related to that imaging aspect. Like gravitational waves, when the first discovery came, they had been talking about merger and all those, right? And the animation goes like two black holes just rotating around. Now, and such case where you have two, like a binary black hole, or else, say for an example, we say that Andromeda has at the center two black holes, two supermassive black holes.
Yeah, that is a possibility.
Yeah, there is a possibility. So, if such cases, if they try to image, how could it look like? Because first of all, the imaging is happening in radio, right? And when there are, like, we are seeing the image for one single black hole,
right?
How it will be when there is a merger or there are two very nearby?
If you have two black holes, in that case, you have to account for lensing by two black holes. That is not an easy task because we do not even have a very good analytical description of space-time produced by two black holes in orbit around each other. Because in gravitation, we have actually solved only a one-body problem. We have not solved the two-body problem. What we can rely on is computer simulations. But computer simulations, because they do not give you an analytical solution, they will essentially be able to tell you about some of the possibilities. You cannot easily explore all the possibilities that may arise. So I'm not sure how strong is the evidence for binary black hole at the center of Andromeda, but yes, possibility of multiple supermassive black holes at centers of galaxies is there, has been discussed quite vigorously over the last 2 decades. I don't know offhand, at least, of any predictions that have been made over there. So sorry, I can't.
Okay, but will there be a possibility that EHT and LIGO will be studying together, like something like a simultaneous? Is it possible? Because both are like a huge
No,
network.
not really, because see, for EHT, the number of sources that they can observe and make a detection is very small, because they have to use telescopes which are spread all over the globe, and the number of sources where they can make such observations is small. Okay, because it's only in a small band in the sky that they can observe with all the telescope or with most of the telescopes. With LIGO, the sensitivity is still so poor that they have to rely on rare events. For example, they have been operating now for 5 years, and they have seen all of around 40 odd events so far. So but when we get to LISA, which is the space version of LIGO in future 10, 20 years from now, maybe then it will be possible to do some simultaneous observations.
Okay.
Yeah. Yes, part of the energy goes in gravitational waves. Yes. Okay. So I'll have to look it up. I don't know about that offhand. Yeah.
Okay, so I don't see any other questions relative to black holes or your talk.
Yeah, I think most of them
Thank you,
were
Yukanshu.
already discussed by Professor. So I think the students can just revisit the video again in YouTube, and everything, almost everything is similar. They just want to go from a black hole to a wormhole and appear somewhere. All right, so continue, Mayank.
Thank you, ma'am. Thank you, sir. Thank you, Yukanshu. And thank you, Professor Baghla, for enlightening us about the theories and black hole and all answering all the questions and explaining it in a way that everyone could understand. Now I request Manish to present vote of thanks.
Yeah, thank you, Mayank. I begin with thanking our distinguished speaker of the session, Professor Jasjeet Singh Baghla, Dean Academics and Professor IISER Mohali, for giving a very informative talk on the public lecture on physics Nobel Prize black holes. We are really enlightened by your knowledge, experience, and presence. We are thankful to our respected Vice Chancellor, Professor K.N.B. Murthy, Register Dr. Puttamadappa, and Dean SOE Dr. A. Srinivasrao for the motivation and support in organizing this lecture. We're thankful to Dean Science and Humanities Professor Deshmukh, all department chairmen, and all the faculties for their precious time. I would like to thank Dr. Radhika D, faculty, Department of Physics and in charge of Ashriya Club for organizing this lecture. A special thanks to all the organizing committee coordinators for making this session a great success. A heartfelt thanks to all the students and viewers for their active participation. With these warm words and a kind message, we move to the end of today's lecture. Thank you.
Thank you. Thank you very much.
Thank you very much, Professor Baghla. Thank you. Thanks a lot.
Okay. Yeah. Bye-bye.
Yeah, bye.
Thank you, everyone.